Okay, so if you look at number 1 here, you have a water bridge, channel of water here over the river that we have here in Germany. And so we give you all these dimensions here, 918 by 43 meters by 4 1/4. Anybody ever been to that bridge? It's interesting, I want to go. It's pretty cool to see boats going around in a big channel of water like that above a river. This is actually probably the last 20, 30 years. I think this was built to commemorate the fall of the Berlin Wall. All those people you see there are just tourists kind of looking at the bridge. Yeah. Pictures in your book. I just thought it was interesting the first time I saw it. I didn't know. It's pretty amazing what we can do. And yeah, this is a pretty nice engineering feat. When I read about it, I thought it was interesting. Look it up, Google it if you want to read some more about it. But imagine this then as just a big container of water there, with those dimensions of 918 by 43 by 4 1/4. Okay? So you have, I'm just going to draw up here, a container here. I'm not going to put all the dimensions on here, but we have just a container. Sometimes I'll draw the fluid like this just to kind of remind you that it's a fluid, just to show that level, but you don't ever have to worry about showing it that way or worrying about any real ripples that you have here in the water. It's just a way to indicate that it is a fluid sometimes when we draw it. Okay? We have 918 by 43 by 4 1/4. Okay. Let's assume this is fresh water, so the density of water is 1,000 kilograms per cubic meter. We want to know the weight of the water, the pressure on the floor of that bridge. Notice there that in part B I said, what's the pressure on the bridge floor? Whenever we ask you for pressure, we're talking about absolute pressures. If I say gauge pressure, then you find the gauge pressure. We're going to actually add a part C to it and find the gauge pressure. But whenever we're talking about pressures, our equations are always absolute unless it says gauge, or unless you actually measured it with something so that you have a gauge pressure. Okay? But we'll add that on when we get there in part C. Okay? So how do we find the weight of anything? Yeah, be more confident. That's one of our easy equations from all semester.
Mass times gravity. Trick question,
W is equal to mg. You all know that. That's what we're trying to find here. The weight of all of this water here. Okay. This is full, so we're going to have this full dimension right here for all that water. Do we know the mass of that water?
You can find it.
How?
You have the density, you could just multiply that by the volume.
Yeah. We're going to do this a lot. We're going to do this a lot with buoyancy. You're going to have to be able to use your densities to find your mass. Sometimes you'll go through and just kind of find your mass, find your volume, do a separate calculation. When we get to buoyancy, there's going to be many times where you really just need to get comfortable writing out mass as density times volume and put it into your equation like that, because there just may be times where you don't have numbers to put in. Okay? You'll see this quite often when we're doing these problems with buoyancy later on. Okay?
So the weight is equal to the density times the volume times gravity?
Because this is just mass now. Yeah.
Okay.
And so that's another way to look at it. We know this here, mass, because density is mass over volume. Then the mass is rho times v. And we're just making that substitution here. There's nothing wrong with going through the calculations and actually solving for what the mass is over here. I'm just saying that there will be times where you can't do that because you don't have numbers. Just know that you're going to see it in this form quite often and be able to write it that way. Whether you get the numbers over here separately or not for the rho and the v to get mass, that doesn't matter, but I'll just write it out here now and put in everything we have. I'll go ahead and show the volume over here. Maybe if you want to get the numbers, the volume is the 918 by the 43 by 4 1/4. You can plug all this in up there if you want to, but I think I wrote this number down if you want it. 1.68 times 10 to the 5th cubic meters here for the volume. So the density is 1,000 kilograms per cubic meter. The volume we just found to be 1.68 times 10 to the 5th cubic meters. and then you have G, your 9.8 meters per second squared. So the weight should come out to be what units? And what is that?
Pressure. What is
A Newton. Force. Weight's Newton. These are forces. These are things we had on free body diagrams. These are just forces here. Remember here, these cubic meters cancel out. You have a kilogram, a mass times an acceleration. That's a Newton. This is just a force. That's all we're looking for here is the force of gravity, the weight force. And then you get 1.64 times 10 to the 9th newtons here for the weight of all that water in the bridge here. Let's find the pressure at the bottom. So up here, I'll just kind of mark it on our diagram that we're going to let this be P naught. We're going to let that be P down there at the bottom. And then this is the H. Here's a case where it's very obvious, I think, to choose this top point here to be the pressure, because that's a place where we know the pressure. I couldn't pick some other point. I don't know how high this would be. This is pretty clear here, where that H will just be the 4¼ meters that we have there. We know the P naught up here is 1.01 times 10 to the 5th newtons per square meter, or you can write that as Pascal if you want to. And then we just take these, put them in up here. Put in your density again. And then that height was the 4¼ This will give us the absolute pressure at that point down there at the bottom. 4¼ meters below the top point, which is at the surface here. And then we get 1.43 times 10 to the 5th. This time I'll write it as pascals. Or you could put newtons per square meter. Doesn't matter which way you want to write that. Is that clear? And then just add a part C here. What's the gauge pressure at the bottom? P is just equal to PA plus PG. So you can use your equation, just solve it for PG. And that's where I keep saying, I keep saying those words where the gauge pressure, just measuring the pressure difference between the absolute and the atmospheric pressure. All we're really doing with the pressure gauge is taking this pressure here and subtracting away the atmospheric pressure from it. Because the pressure gauge measures those pressure differences between the absolute and the atmospheric pressure. And so you'll see here that if we do that, we're really just subtracting off this term right here. And we end up really just getting the rho GH here for that gauge pressure. Sometimes you'll see the gauge pressure just written out as rho GH, because that's what we're doing. We're subtracting away this P naught right here. I'm going to leave it in this form. You can kind of just treat it as an equation like this. But if you're reading the book, sometimes you might see it that way, where it really kind of just writes it in terms of the rho GH, because that's all we're talking about here with this. But let's go ahead and write this out. PG is equal to the 1.43 times 10 to the 5th minus the atmospheric pressure. And we'll get 4.2 times 10 to the 4th pascals there. And these are these places where I was saying, I wrote it this way with the Pascals, just to kind of show you where the confusion might be. And if you don't like the Pascals, just leave them as Newton per square meters. Confusion, I was saying, might be with the subscript here and then all the units here are the PAs. So, it's not usually a big deal, but sometimes if you're not clear on what those are, you get a little mixed up with the different letters and numbers and where they go. So that's it for the gauge pressure part. Any questions about this one?